Welcome to section 2 for chapter 3, where we're going to be computing the null space by elimination. The null space, like what we referenced in the previous section and videos, we're going to be looking at trying to solve this system of equations where I have my matrix A times my vector X is equal to 0, where the null space again contains all of the solutions to this equation. So any vector that solves this equation, the null space is the combination of all of those vectors. So remember that those vectors span essentially the null space. One of the notes I have here with you is if A is rectangular. So again, we're thinking now in terms of an m by n matrix where it doesn't necessarily have to be squared. The book references, and just what I want to highlight is in chapter 2, we focused on a square matrix that was invertible, so that things were a little bit simpler and we didn't have to dig so deep into elimination. That if the rank R was equal to n, then the only solution to this equation was that X had to be 0. The null space only contained the 0 vector. So if we extended our matrix so that it wasn't square, but instead a rectangular matrix, we make sure that the two dimensions may be different numbers. Then if this has rank R, so if there are R independent columns, then out of the total number of columns n minus R vectors would there have to be in the null space. Because if the rank R is not n, then we have dependent columns. And if I have dependent columns, then there is more than just the 0 vector that solves this system. My null space will be more than just the 0 vector. And I was trying to be really careful with my wording. Now back when we were looking in chapter 2, so again, under the assumption that it was square and invertible, we could reduce A into an upper triangular matrix, which we called, I think back in chapter 2, we called it U. And it's where we could factor into L and U. We walked through and looked at the matrix multiplications and the eliminations there, which again we'll essentially use here as well. But the idea is that we'll now extend this by looking at row echelon form, which is what we'll call R. And then ultimately what we'll refer to as R naught, remember this R0 just means rows of zeros, which will be reduced row echelon form. And if you are taking a linear algebra class that's a little bit less conceptual, like the setup is here online, where we'll do some, the videos are primarily focused on how we procedurally solve problems and talk about some of the big ideas. The problems are more conceptual. Typically in an in-person class, you have a mixture, right? You have your conceptual questions, but you also have your procedure of actually performing the elimination. And so that's what we're going to kind of start getting into now. A lot of times the elimination piece is really the starting point in a linear algebra class as an undergrad. But here we're just starting it now in chapter 3. So hopefully with all the terminology and the things that we've learned already, we can kind of build in now, because the elimination piece itself I think is pretty straightforward into the form that we're trying to get into. Now this video is primarily just going to focus on some of the big ideas. In the next part for this section, we'll actually run through a couple of examples for transforming A into reduced row echelon form and then being able to represent the solutions to this equation, in other words, finding our null space. Before we really walk through that process, it's going to be, I think, important to kind of start with, okay, well, what if we are in row echelon form? So let's strip away all the procedure first. If I'm already here, now how do I figure out the answer to the null space? Because we need to be able to do that ultimately. If we can't do that, then there's really no reason to even do the procedure. Right? We need to be able to find that solution. And so that's what I would like to look at. He gives 2 examples in the book that we'll kind of focus on here and just highlight a couple things. That I think is, again, he writes the book very clearly, so if you're following along in the textbook, I think it's easy. But when you don't have a ton of experience with advanced mathematics, I think that's where I wanted to create these videos and kind of create that dialogue as I put myself on our board. So example 1, we're going to look at a 4x2 matrix. A 2x4. Example 1, where we're going to call R, I almost called it A, we're going to call it R. Is already in essentially reduced row echelon form. He's going to refer to it as just echelon form. But the way that it's set up is we essentially have the identity matrix in the first 2 columns And then in the last two columns, we're going to see 3, 4, and then 5, 6. Very challenging numbers. Can't see where you got them, right? 3, 4, 5, 6. And again, the reason why this is kind of reduced row echelon form as well is, and we'll highlight this, is under and above every pivot are zeros. So this has already been kind of cleared out. We'll see in the next one titled "Are Not," the next example, some of the columns are kind of swapped a little bit. But the question is essentially trying to rise here that if I'm setting Rx equal to 0, I need a way to list out the solutions to this. And I want you to notice that this matrix again is a 2 by 4 matrix. It has a rank of 2. So in the definition that we were provided earlier that I had up on the board a second ago, and again you can kind of see in the book, that if there are 4 columns, then if I do 4 minus 2, there should be 2 columns that are linearly dependent. The null space should have 2 columns in its solution set. Those 2 columns will then span the entirety of the null space, because any combination of those will create a 0. We want to figure out how to represent those 2 columns and find those 2 columns. Now, when I'm looking at this matrix and I'm thinking about this as a system of equations, recall that x, when I'm doing this multiplication, is looking at x1, x2, x3, and x4. So if I write out the 2 equations that I have in this system, we have that x1 plus 3x3 plus 5x4 has to be equal to 0. And then we also have that x2 plus 4x3 plus 6x4 also has to be set equal to 0. Now what we're going to do with this is we're going to go through and identify the vector setup and solve this, where when I'm looking at our work, we're going to take x3 and x4, kind of what's referred to as my free parameters or my free variables, and I'm going to set one of them equal to 1, and I'm going to set the other one equal to 0, and I'm going to alternate these 2 things. And by doing the alternation, we're going to figure out what some of the solutions would be to create these zeros. So for example, if I take this setup for the first equation, plugging in 1 here and plugging in 0, I'll get that x1 plus 3 plus 0 has to be 0. Well, x1 is then negative 3. If I plug into the second equation, I get x2 plus 4 plus 0 is equal to 0. And I get x2 has to be negative 4. Notice how that's just the opposite of the x3 variable, the free parameters. So notice then I have a solution set, or I have a solution for x. Excuse me. Not really a solution set, because it's not a list. But my variable, my vector, the variables for my vector, words. x1 is negative 3, x2 is negative 4, x3 is 1, x4 is 0. There's my first solution set. This, if I multiplied it through, creates 0, 0. Negative 3 times 1 is negative 3. That's 0. Plus 3, so I'm still at 0. And 0's out. Notice when I multiply with the second row, 0's out, gives me a negative 4, gives me a positive 4, so 0, and then again, 0's out. So this gives me my first vector that is in the null space. Now again, I should have 2 vectors in this null space because I have 2 columns that are independent, or sorry, excuse me, dependent. 2 are independent, 2 are dependent. So to find the other vector, then I just swap this orientation. Because they're free parameters, and we know that the null space is a combination of these 2, what if we just zero out one of those vectors and we can figure out what they are in their basic sense? So what if this time I went through and I said, okay, well, let's this time let x3 be 0 and x4 be 1. If I do that, then notice what my equations become. This zeroes out, but now this stays. So I now get 0 plus 5. So x1 is now negative 5. Notice how that's the opposite of this entry. For this one, 0's out. I get plus 6, which then when I solve for x2 gives me negative 6. How does the opposite of that entry? And now I have the second vector that's in the null space. -5, -6, 0, and then 1. This now gives me another solution to this Rx is equal to 0. I have two vectors that are in my null space. The combinations of this would span the null space. So this is how we read, once I get a matrix down into echelon form, and specifically even reduced row echelon form, how we can determine these answers based off of my free parameters. Notice, if I'm looking at x1 out of my two vectors, when x3 is equal to 1, notice how this creates the opposites of these two things for 1 and 2. When I want to look at the free parameter x4, how it creates a -5, -6, because that's the opposites associated with my two independent columns, where then I have 0, 1, because now I'm looking at that fourth parameter. So, we have our first example. Now, in this first example, again, I just want you to notice a second observation, again, it's mentioned in the book, but I want you to notice how this is really the identity matrix times some other matrix. So I'm going to reference this in the next video. So again, how the identity matrix is essentially partitioned right here, blocked right at the beginning. And then I have another 2 by 2 matrix F right here on the other side. F, again, can be found here. Like if I put these together, notice -3, -4, -5, -6. It's like negative F. Notice how this forms I underneath. It's just kind of interesting. But a question could arise, well, what if the identity matrix isn't found here? Because what if, instead of x3, x4 being my free variables, what if these two were essentially swapped? What if my free parameter was actually in column 2 and column 4, and my identity matrix was essentially found in column 1 and column 3? And so this is in the second example. So if you look at the next page, essentially, we'll look at the second example here and then round out the ideas of this section overall. If I have another matrix, which again is in reduced row echelon form, the R0 is referencing that there is a row of zeros. So the matrix that we're going to look at now is essentially a 3 by 4. It's how it essentially started, where we end up getting a matrix 1, and I'm going to scroll so I can see it, so I want to make sure I kind of copy down what we have. 1, 7, 0, 8, 0, 0, 1, 9, and then 0, 0, 0, 0. So remember, this R0 includes any 0 rows, anything that completely zeroes out. But notice how that is essentially assuming we are starting with the 3 by 4 and we have eliminated all entries in that third row. But the result, if I notice my pivots here and here, only contain zeros in every other entry point, every other component in that column. And so what I was kind of saying earlier, we see here. I still have 4 total columns, even with 3 rows, still 4 total columns, because that's what we're focusing on. I have 2 pivot points, so there are 2 independent columns here, an x1 and x3 this time. And I have 2 free variables, an x2 and x4. Same situation, 4 total columns, 2 is my rank, so that means there must be 2 vectors that are in my null space. 2 vectors that can create the basis for my null space. Spans. I want to kind of repeat, okay, well, how do we actually find this in terms of the solution, right? Because that's going to be our ultimate goal. If we want to find the null space, how do we find it? When I'm in a form like this, again, we can essentially toss out the 0 row. It's really that simple. We're only going to focus here. And just like before, in terms of my free variables, x2 and x4, we take turns letting them each be 1 and 0. By doing this and looking at the system, we can figure out what each vector should be in terms of my solution set. First row gives me x1 plus 7x2 plus 8x4 is equal to 0. Second row gives me just cleanly x3, plus 9x4 is equal to 0. Notice how the last equation z is equal to 0. It's a true statement. Now if I alternate 1 and 0, so in the first equation, I would get x1 plus 7 is equal to 0. I'm not even going to worry about writing this one anymore. And so we see that x1 is -7. If I plug into the second equation, x3 is 1, x4 is 0. I get x3 is equal to 0. And now I have 1, 2, 3, and 4, so we can create my solution set for the null space. I get my first column, -7, 1, 0, 0. We do this again for x4. Again, the way that we can do that is simply by letting x4 now be 1. We let my other free parameters be 0. When I do that, I get x1 plus 0 plus 8. So again, notice how this is just changing and becoming the opposite. My second equation, we're letting x3 is still here, x4 is now 1. So you get x3 plus 9 is equal to 0. So x3 is the opposite, which is -9. We took the opposite when we were finding it earlier for x3. X2 being 0, or 1 earlier, there was no x2 there. So, second vector, -8, x2 is 0, x3 is -9, x4 is 1. And take a look again what we have in terms of our rows. If I'm focusing on this free parameter, then x1, -7. We don't have any others. For the second row, -8, or sorry, fourth column, -8, and then -9. And then 1. If we take these, all of these combinations, it essentially creates and spans the null space, creating a basis for the null space. Every vector that's a result of that combination is in the null space. All right, it's got to be closed under that multiplication and addition. We have found the two basic vectors that create that space. We call this a basis, and we'll dig more into that later on. So this kind of gives us our second example. Now, again, where this is going. First off, notice how similar this is to the previous reduced row echelon form we had. The only thing that's different in this scenario is that I don't clearly see the identity matrix, and I don't clearly see another matrix for F. But remember, we are allowed to move and permutate this matrix, and it does not change essentially my solutions. It's just relocating where the variables are. I can alter this so that it still fits into a matrix IF and 0, 0 by introducing some kind of permutation. So we can kind of create that same relationship here. So even though these columns are reorganized and we don't clearly see the I, it's really not a big deal in the long run. We just have one permutation that we need to essentially create, find, determine, apply. The trick, and this is what the rest of the videos will be digging into, specifically the next video, we'll be looking at how we use elimination, what that looks like, transforming a matrix into this, is by getting it into reduced row echelon form, we can quickly see the solutions to the null space. If all we had is the identity matrix, then the solution would clearly just be 0. But if I have columns that are dependent, we can start to see how those are creating these free parameter vectors that ultimately span the null space in creating this basis. And so this video hopefully just kind of gives you a lot of the legwork for, again, how we're finding the null space, our ultimate goal. The next video will be, okay, well, how do we get to this? And so we're kind of building on that. So starting with that solution and kind of working our way backwards.